Okay, in this short brief, I would like to introduce the concept of hybrid AI, which means the deep learning and symbolic AI combined, by first providing a brief history of AI and its evolution, as well as some pointers to past literature. More essentially, I would like to delve into the concept of hybrid AI, which combines these two ideas, highlighting its significance in achieving robustness in machine intelligence. Throughout the discussion, I would like to address the following question: how do machines exhibit robustness? Which is a very common and quite popular question in the roadmap of achieving the artificial general intelligence. Some of the terms that I might be keep using might not be perfectly clear to some of you, but I'll try to provide information about these terms as I cover the main material throughout my presentation. I think I'm going to start with the overview of several generations of AI, which is a time course of innovations that led to these generations. In the very, very early days, going back to the Dartmouth College workshop took place in 1956. This meeting was significantly referenced because the team that put together the workshop used what was apparently the first appearance of the phrase artificial intelligence. Anyway, beginning in 1956, the first attempt at AI has been on the symbolic and logical AI domain. This was a natural tendency because humans typically formulate daily problems with objects using symbolism and establishing the associations between the symbols and objects. This trend was mostly knowledge-driven, consisting of mapped symbols and the growing governing rules around these objects. This wave, or namely the first generation of AI, has been quite successful with respect to closed domain applications such as games. Second generation shortly ensued the first and is perpetuated by the inability of the first generation to deal with the sensory input. Be it visual or auditory, such input is full of semantically meaningful information, but comes in extremely complex shapes, unlike the clear-cut descriptions found in the symbolic AI. The most prominent examples of the second generation AI has been the data-driven deep learning models. These models were inspired from the connectome of the brain, in other words, the neural circuitry in biological systems. The connectionist models also marked the birth of the deep neural network frameworks and the fundamental perceptron approach. When we compare these first two generations, we can observe that each address one particular type of intelligent behavior and are not necessarily independent of each other. However, due to their different approaches, one empowered with mathematical symbolism and the other with data, it's quite natural to think of a yet another next generation, or so-called the third generation of AI, which is commonly referred to as the hybrid AI. It's an entity that can learn, remember, and be trained. One of the distinctive features of this generation is the ability to reason about events and go beyond framing associations. In other words, making sure that the model makes causal reasoning about what's around. Of course, any hybrid approach would not necessarily lead to emerging behaviors such as consciousness or other traits that humans acquire over their lifetime. Therefore, it is likely to expect a fourth generation AI to appear in the near future given the circumstances. Let me briefly dive into these generational changes and associated approaches to AI. Symbolic AI, the very first examples of intelligence modeling efforts, which is a symbol system adapted as the model of human higher mental activity. Symbols are typically characterized by compositionality. Simple atomic symbols may combine and form complex symbol sequences, such as found in the foundations of language. From 1965 to 77, first examples of the symbolic AI had appeared. They were too simple and far from practical. Symbolic AI has obvious limitations. To name a few, they can only solve deterministic problems with complete information in structured environments. An example is perfect information games, such as chess. Human cognition or human cognitive behavior, on the other hand, usually takes place in a complex situations with an imperfect information. One other difficult problem encountered by symbolic AI pioneers come to be known as the common sense knowledge problem. In addition, areas that rely on procedural or implicit knowledge, such as sensory motor processes, are much more difficult to handle within the symbolic AI framework. In these fields, symbolic AI has had limited success and by and large has left the field to neural network architectures. The essence of the problem was knowledge representation. In other words, some of the knowledge representation methods, such as production rules, laws of logic, are easy to be implemented and streamlined by programmable computers. However, such rule-based representations are quite limited in their expression, and due to that, they fail to describe complex and uncertain knowledge. Since the math tools for processing discrete symbols and infer their compositionality is missing, only the math-complete procedures and logic programs were available in classical computers, and hence making the implementation of knowledge-driven strong AI very, very challenging to implement. Here I've also provided several examples on the left that I can find in the literature relevant to symbolic AI and its development, including the AI winter, which happened between 70s and 1908. And it's also mostly due to the absence of computational tools to deal with sensory information. Second generation of AI concerns with the processing of the sensory information in humans, such as vision or audio. There are two conceptual paradigms here. The first posits that the information is encoded in memory, often implemented through neural networks, and aligns with the symbolic AI approach. The second and more popular perspective asserts that sensory stimuli are not stored in memory, but instead from stimulus-response connections or channels in a network of neurons. This viewpoint, known as the connectionist claim, forms the basis of connectionist AI. This branch of AI has incredible rich literature, as I was not able to include all of the groundbreaking work here in my presentation. Historical record probably goes back to Newton, since the current efficient implementations of optimizing machines is based on derivatives, or more broadly, the calculus. The first model, however, was proposed only in 1958, called the perceptron. There were two motivations behind it. First is the published math models of neurons, such as threshold circuits. And obviously, the second one is the Hebb's learning rule, meaning that neurons fire together, wire together. The founders of symbolic AI, or more generically, all of them were aware of the idea of connectionism from the very beginning. For example, McCarty, the founder of perceptron, asked questions like, how can I set set of hypothetical neurons be arranged so as to form concepts of higher level of abstractions? Obviously, the perceptron has only one hidden layer, which is too simple, which makes it impossible to segregate linearly separable data. Even if the number of hidden layers is increased, it's difficult to use the perceptron because there was no efficient learning algorithm at the time. When we gauge the developments up to 1980s, we began seeing the primitive models of convolutional neural networks, or recursive neural networks, and dynamic bias networks. And more advanced models followed, such as AlexNet, LSTMs, and ResNets, and a notable success of a connectionism such as AlphaGo and ChatGPT, to name a few. Consider an example: supervised learning training. In that setting, for a given data set, for example, samples, multidimensional samples with labels coming out in a space product of two sets, we estimate an input-output function to estimate the parameters theta to minimize the expected loss for a given loss function. The typical approach to the optimization in here is based on a technique called backpropagation, irrespective of its similarity to how human brains learns and optimize its memory and neural connections. Note here that the model is defined by the architecture and parameters, and this is more broadly known as parametric learning in literature. There are three basic assumptions in parametric learning. One, independence. The selection of the loss function and the neural network structure or architecture are data independent. Second, large capacity, which means there's a huge number of samples, in other words, enormity of the data size, and which is a requirement. Finally, completeness. The training samples are complete and noiseless examples of the realism. If all the assumptions are satisfied, then the mapping function will eventually converge to the optimal mapping function f, as we have an increasing number of training samples. Remember that backpropagation doesn't necessarily find the global minimum or global optimum in the non-convex error landscape. Also, due to the universality of connectionist architectures for enough data samples, we can guarantee the right approximation of any learning function. On the other hand, there are serious limitations. One, vulnerability of neural networks to imperceivable noise added to the input test data, which also actually brought on, carry on, and different fields of AI like adversarial learning. In other words, neural networks seem to be quite brittle. Second, one important hypothesis here we can propose is that if the input data becomes incomplete or degraded in any way, then the architecture will likely to be dependent on the nature of the data. And thirdly, as we can observe, the other limitations, and maybe the most discussed these days, is the black box interpretation of the neural networks, which constrains the network of connections interpretability. In fact, this limitation has led to a brand new branch of research called explainable AI. And fourth, one of the desirable properties of connectionist models is to develop inherent invariant representations, which helps with the generalization capabilities. Unfortunately, building large breadth of invariance within such networks is very, very challenging and may require unique changes in the training regimens. And there are dozens of examples that demonstrate the serious limitations of the second generation of AI. Two of them are presented here. One is COMNETs under degraded imagery, and the large language models, which are hallucinating about the data they ingested during training, which leads to logical errors, inconsistency, limited reasoning, and toxicity. Regarding the human and computational intelligence, I would like to also mention Marowick's paradox as an observation came forth by AI researchers Hans Marowick, Radney Brooks, and Marvin Minsky, that tasks that are easy for humans, such as recognizing faces or understanding language, are often difficult for computers, while tasks that are difficult for humans, such as mathematical calculation or modeling or processing large amounts of data quickly, are often easy and trivial for computers. This paradox highlights the disparity between the human and artificial intelligence capabilities, suggesting that the skills that humans find easy to perform are not necessarily the same skill set that are easily programmable into the machines. A famous quote from Minsky highlights this paradox very well. It is comparatively easy to make computers exhibit adult-level performance on intelligence tests and playing checkers. However, they're very difficult or impossible to give them the skills of a 1-year-old when it comes to perception and mobility. Among many intriguing questions related to Marowick's paradox, these three struck me the most. How can insights from Marowick's paradox help us develop future AI systems that are experts in tasks traditionally considered difficult for computers, such as common sense reasoning or emotional understanding, or even recognition under extremely severe, unfavorable conditions? One avenue for exploring to attain how human-level performance could be fusion of the strengths of symbolic reasoning and the pattern recognition abilities, the most recent deep learning revolution. However, the methodologies for fusion is subject to further investigations. Finally, a more fundamental question arises. Can Marowick's paradox be even resolved? Or is it an inherent limitation of current AI technology? The most recent development certainly assumes exact reverse and attempts proposing ideas to overcome the challenges posed by Marowick's paradox. In conclusion, the fusion of symbolic AI and deep learning algorithms known as hybrid AI or hybrid AI represents a promising direction in the field of artificial intelligence. By combining the strengths of symbolic reasoning, which excels at logic, reasoning, and knowledge representation, with the pattern recognition capabilities of deep learning, hybrid AI systems can potentially achieve more robust and versatile intelligence. This integration allows for the development of AI models that can understand complex relationships, learn from vast amounts of data, and reason about abstract concepts, leading to more sophisticated and human-like AI systems. However, challenges remain in efficiently integrating these two paradigms, including addressing issues of interpretability, scalability, and robustness. Nonetheless, the pursuit of hybrid AI or hybrid AI holds great potential for advancing the capabilities of AI systems, making them more robust and solve complex real-world problems across various domains. Thank you.